Hey everyone, welcome to our next lesson in our unit on electricity and magnetism. Today we're going to be learning about electric circuits. We'll split this up into a couple different videos as we're going to learn about a couple different kinds of circuits, both series circuits and parallel circuits. And today we're mostly going to focus on series circuits. Now these are electric circuits that are going to be used in any type of electrical device, whether it's a handheld device, car wiring, wiring that you'd find inside your home or in a building. They're all going to be related to one of these types of circuits, either series or parallel. So it's simple, and we will pretty much just focus on simple electric circuits here for the most part in this class. But the simplest electric circuit always has to consist of some type of source of electrical energy. And oftentimes this is usually supplied in the form of a battery. In the case of your house, this would be supplied from the power company, which would be generating it through a generator or collecting it somehow via solar panels or some other means. It's going to consist of connecting wires that are going to connect our components and bring current from the battery or from the source to each component and then back. And some type of circuit element, something that we're going to be using to power to do something within this circuit. And this could be within the scope of this class, what we call a lamp or a light or a resistor. These are two of the more common components that we'll see in our circuits within the scope of this class. Now what we'll focus on for today are series circuits. And a series circuit is real basic. It's a circuit in which all parts are connected end to end. And what that does is it provides just one path or a single path for current to flow. So where current's being generated or stored in a battery to run on an electric circuit, to run some type of device on an electric circuit, there's only going to be one path for that current to flow. And if we can think of that like the river or a creek, there's no branches of the creek. It's just one single path down the river. There's no side chutes or anything like that. Just one path for that water to flow. Which if you think about most rivers, it's probably the case for most of them. As you have maybe different inlets and things like that and different creeks feeding a river. But the series circuit is we said has to consist of a battery. And I'm going to use the schematic symbols from your reference table, which are on the bottom of page 4. I'm going to start here with a battery, and a battery we know has multiple cells. So there's my battery. So we have to have a battery. We have to have connecting wires. And we have to have a circuit element. So here's our connecting wires. I'm going to put in a resistor, which is this kind of little lightning bolt thing. I'm going to put 3 of them in here. Mine are not always the prettiest. So there's our single path for current to flow. So this is the basic series circuit. As current's generated from the battery, we're going to see electrons move throughout this circuit and back to the battery. So that's going to be our current or a flow of electrons throughout this circuit. I'm going to call each one of these resistors R1, R2, and R3. So we have 3 different resistors. Those are our circuit elements, battery, and our connecting wires that are connecting everything end to end. Now each of these resistors together we think of this circuit as a whole, there is a certain voltage being supplied by the battery, there's a certain current flowing through the circuit, and there is a specific or definite amount of resistance based off of the wiring, the battery, and the resistors mainly itself. There's going to be very little resistance generally within the connecting wires and then the battery itself. Now the equivalent resistance of this circuit is going to be the single resistance that would replace all three of these resistors in this circuit. And there's a way that we can figure out what that is. This is going to be different depending on the type of circuit. I'll give this to you in a series of equations. Now the current, if you think about this flow in a river, the current here, since there's only one path, the current is the same anywhere in this circuit. So at resistor 1, we could have, let's say, we could call the current flowing through that resistor, we could call that I1. Just like the current through resistor 2, we could call that I2, I3, and so on. But the current flowing through each of these is the same. So the current in a series circuit, I'm going to put RTS for remains the same. Current remains the same in a series circuit. Anywhere in that circuit, if you only have one path, the current's going to remain the same. The voltage, however, is going to be different depending on the type of resistance in the circuit. Now through resistor 1, we could have current 1. We could also have voltage 1. Through resistor 1, voltage 2 through resistor 2, voltage 3 through resistor 3, and so on. This will just depend on how many circuit elements we actually have in the circuit. Now the total voltage here, indicated by V, would be the sum of each of the potential differences across each resistor. So the sum of potential differences of all resistors. So the voltage drop, or the potential difference across each resistor, has to total up to the voltage that's coming from the battery. We're going to have some voltage there. That's going to be the supplied potential difference across the entire circuit. Now the resistance of this circuit, this one is kind of intuitive, but the total resistance, or the equivalent resistance, is the single resistance that could replace the several resistors. Well, we have resistor 1, resistor 2, and resistor 3 in this circuit, and so on. We could have more than that. But the sum of each of these will give us the equivalent resistance. And that's the sum of resistance of all the resistors. Now resistors could be replaced by a lamp, a motor, something that's going to be using current that is going to provide some type of resistance to the flow of that electricity. Generally, resistors are used in circuits to change the amount of voltage or current, or to adjust things for a particular reason to achieve some type of desired outcome, whether that's powering a certain device, changing signals or current in the circuit to do something. Could be a number of different things. But we will see a lot of resistors. I'm going to do an example here, and we'll look for each of these three values: current, voltage, and resistance, which we know as Ohm's law, which we learned as the ratio of our potential difference to our current. I'm going to rearrange this because in the circuits here, the current is equal to the voltage over the resistance. And this is the one I seem to use. We could use this in any form, but this one is good to use for series circuits. So I'm going to do this example here where we have 3 resistors with resistances of 1 ohms, 3 ohms, 5 ohms. They're connected in series to an applied potential difference of 27 volts. So it's the same idea here, 3 different resistors, 1, 3, 5 ohms, and the battery here would be, or would have, a potential difference of 27 volts. When I put this together in a circuit here, we have, I don't think I can move this entire thing. There's a lot of different items in here. Okay, we have our cell here, which if I show this in a different way, you can probably see it a little bit better. Our battery here looks like a copper top Duracell. 1 resistor, 2 resistor, 3 resistors. We have resistors of 1 ohm, 3 ohm, and 5 ohms. You can see the color bands on here are different, and those colored bands indicate the resistance in each of those resistors. That's how we can determine what the resistance is there just by looking at it. Connected in series, we only have 1 path for the current to flow. We can see that conventional current flowing there. I have this unconventional current to an applied potential difference of 27 volts. We got our battery here, which is supplying the difference of 27 volts from high potential to low potential. And that's how this positive charge is moving from high potential or positive potential to low potential or negative potential. Now if I switch this, this is conventional current. What we call electron flow theory is how current would flow as if we treat it as if it was electrons, which are negatively charged. And they're going to flow from a source of negative potential, where they're attracted to a source of positive potential. So it's the opposite direction of flow compared to conventional. But this is how we generally treat current flow in this course. Electron flow theory, flowing from negative potential to positive potential. So I'm going to leave this like this for now. Let's find the equivalent resistance in this circuit. I'm going to switch this over so we can look at this schematically. So here's our resistor, and again, this looks just like our circuit here. We got our battery, 1, 3, 5 ohms. These are not in a row like they are in our notes here. We could change that easily, but it doesn't really matter. We could put this in a number of different ways. We could put this thing here. We could put this thing here. It doesn't really matter because we still only see one path that our current's flowing through. So I'll leave it like this. Maybe I'll pull this battery in a little bit so we can see it a little bit better. So our battery there, and our current is flowing. So we see that the equivalent resistance, Req, is equal to the sum of each of the resistors in the circuit. In this case, we have 3. Resistor 1 was 1 ohm, 2 was 3 ohms, and 3 was 5 ohms. Doesn't really matter the direction in which we do this. This is going to equal 9 ohms, which equals our EQ, our equivalent resistance. Determine the current through each resistor. Well, we measure current with an ammeter. We'll have more about this later in a later video, how to use these meters. But basically, we can insert this somewhere in the circuit here. And again, you can use these simulators to help with any of these questions. Set up the circuits. These are really nice. We can change the values of the voltage here. We can adjust the resistance of each of these. So these are really handy to use. You can see that one there. As we change this resistance, the current is changing. Now at any point here, to determine current, well, we know current remains the same in a series circuit. So the current through each resistor should be the same. Like I mentioned up here, let's use our alternate form of Ohm's law for series circuits. We know that the current through each resistor is going to be the same. So let's use Ohm's law to determine what that is. And we'll use the ratio of the voltage supplied by the battery across the resistance. Now this is going to be our EQ. Just want to verify that. Our voltage from our source is 27 volts. The equivalent resistance we calculated right above was 9 ohms. This gives us a current of 3 amps. And that's what we measured here. Now just to kind of verify, the current flowing through, we can call this resistor 3, is 3 amps. Through resistor 2 is 3 amps, and through resistor 1 is 3 amps. And anywhere we put this in here, we should have the same current. Notice that we have to be on the circuit in order to actually measure this. Okay, but anywhere here, we're going to have a current of 3 amps. And this is the same for all resistors. And you can go through and label that for each one if you'd like. I'm going to put a little notation in there that it's the same for all resistors. C wants us to find the potential drop, otherwise known as voltage, across each resistor. Now we know that the total voltage here, 27 volts supplied by the battery, is equal to the potential difference across each resistor, or the voltage across 1 plus the voltage across 2 plus the voltage across 3. So to do this, we'll use a form of Ohm's law where V equals R times I, the resistance times the current. That'll give us the voltage across each resistor. So I'll do this first for V1. The voltage across the first is equal to the resistance of the first resistor times the current of the first resistor, which we know is going to be the same. So we don't have to call that I1. I'll leave it as I1, but we can just call it I because it's the same. This would be 1 ohm. That's 1.0 ohms times 3.0 amps. Again, that's the same at any point here. So the voltage would be 3.0 volts, and that's for V1. I'm going to do the same here across for V2 is equal to R2 times I2, which is going to be 3 ohms times 3 amps, which gives us a voltage of put that in there as 90. 9 volts. This would be V2. And V3 is equal to the resistance of R3 times the current through R3. And we have 5 ohms times our same current. And V3 is equal to 15 volts. We have 3 answers here. And this one was V1. Those are our 3. Now, according to Ohm's law, 27 volts at the source should equal the total of each of these, 3, 9, and 15. And 3 plus 9 is 12, and that's 27 volts equals 27 volts, so that checks out. Now we can verify this with the simulator. We'll use our voltmeter to measure voltage, our original. And we can measure this. Notice how we don't get a reading until we insert the other peg here. Across the battery, and we can read what our voltage is. 27 volts. Now that's completely across the battery. We can shift this to here. And that's the potential difference being supplied by the battery. Now we can check this by moving our leads here to measure the voltage across the resistor. Notice how that didn't change. I'm going to move the negative lead here across the first one, and we know that this should be about 3 volts, and that is exactly what it is, 3 volts. And that was our V1. V2, using our 3 ohm resistor, we said was going to be 9 volts. Let's check that. So a way to move these around. Leave that there. We'll go across this one, and we get 9 volts. That's a total of 12 volts right there, and we can measure that. If we bring this guy back here, and we measure the total voltage drop from our battery across the 2 resistors. Just like if we were to add the third in there, it would be 27. Well, let's measure it just across the resistor here. So we move this lead back to here, and it is 15 volts. Notice how this is not directly on the resistor, but the only resistance in between these 2 points is that resistor. So if we move this closer, the value doesn't change. It's still 15 volts, as we had determined from V3 over here. And each of these voltages added together equals the total voltage or total potential difference supplied by the battery. I'll give you guys some practice with this. Make sure you're asking any questions if you have them. The next part of our lesson will focus on parallel circuits. But for now, let's focus just on series circuits. If you have questions on any of this, let me know. Otherwise, I hope everyone has a very nice day.